Okay, let's get started now. So there's no one here, but that's so good. Anyways, so first question. I'll pretty much go through what this paper's looking like right now. So a few partial differential questions, Laplace transform. Did I even do the Laplace transform questions? Oh, I forgot. That's fine. Fourier series. Another partial differential, Taylor estimation. Vector fields, ODEs. Then there's also, what is this? Extreme values, matrices, another Laplace transform question, double integration, and then finally this long, really long PDE question. So I'll just start going through it one by one. Should I do it on the iPad? Because I don't know if they can see. Zach, but I'll just do it on my iPad. I'll just sit down here. Yeah, I'm using Discord to know. Yeah, okay. Cool. I'll just use that then. Okay. I'll take a seat. Let's see if the recording's still going. Oh, it is. Okay. So, for our very first question, we can use chain rule. However, the chain rule is really long, and you're going to have to use product rule at some point. So that's if you do like delta squared z over delta r squared is equal to, I don't even know the formula because it's really long. So what I'm going to do, I'm just going to sub in x and y into our z equation, and then I'm going to use normal differentiation just to differentiate z with respect to r and s. Okay. So, firstly, z is equal to 4r plus 4s all squared minus 4r minus 4s all squared. Okay. You can differentiate this straight away. However, I'm going to use the difference of two squares rule. So pretty much, if you have something like a squared minus b squared, you can make into a plus b and a minus b. I'm going to use that real quick to simplify our z equation. I didn't do that in my solutions, but I think I've just realized, and it makes it much more simple. So you get a, let's say this is our a, this is our b squared, a plus b, you get 8r, a minus b, you get, what is that? A minus b, you get 8s. So in total you just get 64 rs. That seems wrong. Yeah, that seems very wrong actually. Okay. Yeah, no. A minus b, 4r minus 4r, 4s plus 4s, so I'm going to do it the proper way. Okay, so delta squared, first of all, delta z over delta r. I'm not going to do the difference of two squares rule, by the way. I'm just going to straight differentiate it. Since we're differentiating with respect to r, we don't really care about the 4s here, right? We can treat it like a constant, right? If that makes sense. Because you're dealing with a function of two variables. So let's say f of x y is equal to x squared plus 2y squared. This is a function of two variables. If you want to differentiate this just with respect, because it's a function of two variables, you can partially differentiate it with respect to one variable, and you can pretty much treat, so for example, if you're differentiating with respect to x, you can treat the y term like a constant. Right? In this case, I want to treat the s term like a constant, and you end up getting 2 times 4 times 4r plus 4s using chain rule, minus 2 times 4 times 4r minus 4s. Okay. Differentiating this again with respect to r. R squared. You get 2 times 4 times 4 minus 2 times 4 times 4, and both of these cancel out, so you just get 0. Okay. Pretty simple. This is the same shit from, same stuff from Math 1B. And so I won't bother going through these. I'll put up the solution here. I'll just quickly go through my solution. Differentiating z with respect to s, you can see there's a 4s as a coefficient of s, so we can just take that to the outside when we're differentiating it once. And same thing here, minus 2, the 2 comes down, multiply by the 4, and then you can just take 1 away from the power. So 2 minus 1, you're just left with 1. Right? And when you add it all up, you get 64. Wait a second. Minus 8 times that. Oh, sorry, this is 0. Oops. Yeah, this is 0. Yeah, so actually, the the difference of two squares method does work. So I'll quickly go through that as well. A squared minus b squared is equal to a plus b, a minus b. Oh, well, in this case, y squared minus x squared is equal to y minus x, y plus x. And so this is pretty much equal to y minus x. You get why would we do y minus x? Goodbye, bro. Y minus x. And you got minus as times y plus x. You just get 8r. So you're left with minus 64sr. And when you differentiate this twice with respect to s or r, you end up getting 0. Alright. And for the last question, you just get minus 64, because when you differentiate this once with respect to r, you get minus 64s. So for example, you get this with respect to r, you get minus 64s, and when you do this again with respect to s, you just get minus 64. Okay. I guess that's a shorter way of doing that question. Okay, Laplace transform. Let me quickly pull out this table over here. Oh, wrong table. This table over here. Okay. So what I'll do is get rid of this stuff because I already went through it. And I'll go through the Laplace transform question now. So we're trying to find the Laplace transform of e to the power of t over 4. T over 4 times cos of 2 theta. Sorry, cos of 2t. Is it still recording? Yeah, okay. Okay, now we're going to take a look at our table here. Okay, so we are using this rule over here. So we have e to the power of minus at times a function with respect to t, and pretty much this one over here correlates to this one over here. So this is called the shifting theorem. So what we're going to need to do, first of all, let's identify what a is. In our case, a will be minus 1 over 4, and our f of t is equal to cos of 2t, right? And this is equal to f of s plus a, or s minus 1 over 4. Okay, but what is f of s, or what is f of s minus 4? Oh, f of s minus 1 over 4, right? First of all, we know that f of s is equal to the Laplace transform of f of t, right? And then we can pretty much just substitute in s minus 1 over 4 for s. So I'll quickly show you what I mean. So let's substitute some things in. The Laplace transform of cos 2t, using our table again, cos of 2t, so we're going to need to use this formula here. So you get s over s squared plus b squared, sorry. So if our b is equal to 2, you just get s all over s squared plus 4. And now if you want to find f of s minus 1 over 4, you can just replace your s. So replace s with s minus 1 over 4. So this is pretty much just s minus 1 over 4 over s minus 1 over 4 all squared plus 4. So this is equal to the Laplace transform of e to the t over 4 cos of 2t. Cool. I wish I had some students so I can ask some questions, but it is what it is, right? Hopefully that makes sense. If not, look over your lecture notes. I'm pretty sure the lecturer does a pretty good job of explaining it as well. Second question, the inverse Laplace transform. Okay, so we're trying to find an inverse Laplace transform of e to the power of 4e to the power of minus 3s divided by s squared plus 14. S squared plus 16. Okay. First of all, my first thought is to kind of break it up. So you get inverse of e to the power of minus 3s times 4 all over s squared plus 16 right, and we're gonna have to take a look at our table again, see what kind of corresponds to our equation here, or our expression there. So my first thought is to take a look at this one over here, this Heaviside function. Alright, so we have e to the minus cs over here, and we also have an f of s over here. So I'll just say e to the minus cs is equal to e to the minus 3s. Therefore, our c is equal to 3. And our f of s is equal to 4 all over s squared plus 16. Alright? This pretty much corresponds to this one over here. So this sine of bt. So if we take the Laplace transform of sine of bt, we get f, or capital F of s, being b over s squared plus b squared. So in our case, if we have b is equal to 4, we'll get this to be 4 all over s squared plus 16, which is exactly what we have here. Alright, let me just check. Yeah, that's right. So now going back to this, if we want to take the inverse Laplace transform, we're pretty much trying to get a function like this. So first of all, what we have to do, we have to find what f of t is, right? Because we already know what c is, yeah? It's equal to 3. F of t is equal to the inverse Laplace transform of f of s, okay? And we've pretty much already done that. We've already said that it's equal to sine of 4t, right? But then how do we find f of t minus c? Going back to what I said before, you're just going to have to replace our t. So I'll quickly show you what I mean. So therefore, we can say that f of t is equal to sine of 4t. F of t minus c, or t minus 3, is equal to sine of 4 times t minus 3, which is equal to sine of 4t minus 12. Okay, and our u function, it's called the Heaviside function, we just leave it as it is. Okay, we don't really touch it. So we can say that the inverse Laplace transform of e to the minus 3s times 4 all over s squared plus 16 is equal to sine of 4t minus 12 times u of t minus 3. That's our answer. Laplace transforms are pretty repetitive, so you can just keep practicing small questions like these, and I'm pretty sure you'll get good at it. There is a harder example that I'll go through afterwards. It's to do with partial fractions, and I'll go through that as well if I have time. Okay. So that's the first question of the 2023 Term 3 paper, and I'll just be pretty much going through the rest of the paper now. Okay, next. Hey. Question 3, or should be question 2. Consider function h defined by this function, a piecewise function. We periodically extend the function h in an even manner. So even manner is very, very important. For minus pi to 0, the Fourier cosine series is given by h of x equal to a0 plus the sum from 1 to infinity of an cos nx. Find the Fourier coefficients a0 and an by evaluating the relevant integrals. Just a note, the integrals are kind of long to solve, but they're not difficult. They're just long, okay? So what I'm gonna do, I'm gonna first draw the function h of x, and I'm gonna periodically extend the function. Okay, so let me draw up the function. Okay, so let me say this is pi, this is pi on 7. Alright, so so between 0 and pi on 7, our function is equal to 0. So open circle equals to 0. And then at x equals to pi on 7, our function is equal to, what is that? 6 pi on 7 here, and then at x equals to pi, it's equal to 0. So I can just draw a straight line down like this. But this is 6 pi over 7. Okay, and now if I want to extend this evenly for minus pi to 0, so where this is 0 over here, because it's an even function, or we're reflecting it in an even manner, you can just reflect it across the y-axis. Okay, if it was an odd manner, then you'd have to rotate it by 180 degrees, right? But since we're doing it for an even manner, you're gonna have to reflect it across the y-axis. So for example, this is what it'll look like. Oh, sorry, this should be open circle. This should be an open circle, right? Yep, open circle. Where this is minus pi on 7. Okay, you see how if there's an axis of symmetry across the y-axis, alright, this point corresponds to this point corresponds to this point. If it was an odd manner, then I would have to flip this function 180 degrees, so it would come down here, over here. So it would look something like this. I'll do it in green. It would look like this. That's a terrible diagram, but it's fine. Because the function it's a bit harder to draw. I think that's why the question really asks for an even manner. But this is all we need to worry about. So now that I've periodically extended it in an even manner, we can find what the period is. The period would be 2 pi. 2 pi over here, and therefore, and this is equal to 2l, so l is just equal to pi. This is very important when we are evaluating the integrals, and I'll quickly show you why. So to find a0, a0 is equal to 1 over 2l from minus L to L of just f of x, okay? So this is just pretty much equal to 1 over 2 pi from minus pi to pi of our function f of x. Now, the reason I write just f of x and not the function pi minus x is because it's not exactly defined throughout this whole thing properly. There are some discontinuities, and what I'm going to do firstly, actually, because our f of x function is even, the area between 0 and pi is equal to the area between minus pi and 0. So I'm going to kind of make the bounds a bit simpler. So I'm going to say 2 over 2 pi from 0 to pi of f of x dx. Okay? So this is just equal to 1 over pi. And for our lower bound, I'm actually going to write pi on 7. Okay? And then I can write pi minus x dx. The reason why I write pi on 7 instead of 0 is because between 0 and pi on 7, our function is equal to 0. So I can kind of write it a bit neatly, actually. I write it like this. Alright, between 0 and pi on 7, 0 dx plus pi on 7 pi of pi minus x dx, where this function will just be, or this integral will just go to 0. Alright, so now if we're trying to evaluate this integral over here, you get 1 over pi of the integral from from pi on 7 to pi of pi minus x dx. This is just equal to 1 over pi x minus x squared on 2 between pi and pi on 7. I'm not going to bore you with the whole solution, so I'm just going to skip to what the answer is. 18 pi and 49. Okay, so therefore a0 is equal to 18 pi on 49. Cool, so that's how we find a0. A few things to note: even function, alright, and that's why I times the area by 2 over here. So I've cut the bound in half, but the area I've multiplied by 2, okay? And then between 0 and pi on 7, our function is actually equal to 0, so we can pretty much just omit it. We don't really need to worry about it. And we just really care about the function between pi on 7 and pi, okay? And we can just integrate that. Alright, next, an. Okay, this is actually really long, but I'll go through the theory behind it. An is equal to 1 over L from minus L to L. I think this will be on the formula sheet, so you don't have to really memorize it. Of f of x times cos n pi x all over L dx. Okay, as already discussed, L is pi, so minus pi to pi of f of x cos of nx dx. Okay, now another thing to note again, this function f of x times cos nx is even, because f of x is even and cos of nx is also even. So because both of these functions are even, our overall integrand is even. And I'm going to multiply the integral by 2, but the bound, I'll cut it in half. So 2 over pi from 0 to pi of f of x cos nx dx. Okay, and again, pi on 7 to pi, because between 0 and pi on 7, our integral is equal to 0. So I'm going to do pi minus x cos nx dx. As you can see, we're going to have to do integration by parts at some point or another, right? That's the solution. Okay. Hey, I'm gonna quickly do this integral over here. So we have an is equal to 2 over pi from pi on 7 to pi of pi times cos nx minus x cos of nx dx. So I've expanded the integrand. I'll probably do it part by part. So I'll do this integral first, and then I'll do this integral second. Okay. So I'll call this 1, and I'll call this 2. 1. So you get pi times, integral of pi on 7 to pi of pi cos nx dx this is just equal to pi times, when you integrate cos, you get positive sign, so you get sine of nx divided by n from pi to pi on 7. So you get pi times sine of pi x minus sine of n pi on 7. So not pi x, sorry, n pi all over n. And one thing to note, sine of n pi is always equal to 0 for any n value. So this is for all n within the integers. Yeah. So for all integer values of n, right? So I'm just going to say this is equal to 0, and you get pi over n minus pi over n times sine of n pi over 7. Cool. Now the second integral is actually the long one. Okay. So we're dealing with the integral of x cos nx dx between pi and 7 and pi. Okay. I'm going to use something called the implicit substitution method, but you can just use DI method or just normal integration by parts. So writing out u, v, u dash, and v dash, and putting it into the formula. I'm going to do a quickly faster method called the implicit substitution method. Pi x and then d of sine nx all over n. So no matter what you do, you still get the same answer. So pretty much what I'm saying is that when we differentiate this with respect to x, this function over here, you end up getting cos nx, right? And this is in the form of u v dash, which is what we're doing by parts, and you get u v minus what? V dash u? No, sorry. V u dash. Yeah. So I'll quickly show you. I'm just gonna plug it in. So you get x sine nx all over n between pi on 7 to pi minus pi on 7 to pi of sine of nx of n dx. Okay, I'm not going to teach you guys what integration method I just taught you. Just know that no matter what method you use, you're going to get to the same answer, right? You will especially get to this point for sure. Okay. It's just I've just skipped a few steps. This is now equal to pi of sine n pi minus pi on 7 sine of n pi on 7 divided by n minus, when you integrate sine, by the way, integrate sine, you get minus cos. Okay, so this is just equal to, I'm going to make the minus into a plus because the minus and the minus cancels out. Oh, they don't cancel out, they just become a plus. and you get cos of nx all over n squared between pi on 7 to pi. Again, sine of n pi is equal to 0, so that will just cancel out, and you're left with minus pi sine pi over 7 divided by n plus cos of n pi minus cos of n pi over 7 divided by n squared. Okay, Q. Now, this we can actually simplify it down. So we can say, but cos of n pi is equal to minus 1 to the power of n. This is something that was covered in the lectures. So I'm just going to simplify this down and make it into minus pi. I'm missing something. There should be a 7 here. Minus pi sine pi over 7 pi over 7n divided by 7n plus minus 1 over n minus cos pi n over 7 divided by n squared. That's the integral. It looks very disgusting, but it's correct. Okay. Now to find a of n. 1 over pi times that first integral, you get minus pi over n sine n pi over 7. Then you do minus pi over 7n times sine n pi over 7 plus minus 1 to the power of n minus cos n pi over 7 divided by n squared. Okay, now what? I'm just going to leave the 1 over pi on the outside. Okay, and you're left with this becomes a plus, so this becomes 6 pi over 7n sine of n pi over 7. So I'm just combining these two terms together, plus cos of n pi over 7 minus 1 over n to the power of n squared. Done. That's our an expression. Really long expression for an. Let me check if this is correct. Yes, that's correct. Oh, I'm missing a 2. Oh yeah, I forgot the 2 over pi, sorry. It should be a 2. Cool. That is a Fourier series. That's probably not as hard as it gets, however. I have seen some harder Fourier series questions. Okay. Hey, time to go over this last part. Well, we've pretty much already drawn out the final one, but I'll go through each of them individually. So, which of the following is the even periodic extension of h of x over minus 3 pi and pi? So, our first function was, our original function h was just between 0 and pi, and we can see it's over here, right? As we drew the even periodic function, we knew that it looked something like this. So it can't be a, so it can't be this. Right. This is whack beyond belief. Oh, actually no, it's not. There's like a axis of symmetry over there. Yeah, there is, but obviously our axis of symmetry is at 0, or at the y-axis, sorry, because it's an even periodic function. This, I don't even know what the hell's going on. And this is what we pretty much drew. So it should be part D. Okay. So what we drew earlier was this. And what they've done with a period of 2 pi, they've just copy pasted this over here to the other side. So they've copy pasted it here, and they've copy pasted it here. Oh shit. They copy pasted it here. Cool. That is question 2. When do I finish, by the way? 2 o'clock? Okay. No response. So I'll delete this page. Time to move on to the second question. Third question, sorry. Okay, now this first question over here is constructing a Taylor series up to the quadratic term for a function. In this course, we only look at Taylor series up to the quadratic term. We don't look at the cubic term or the quartic term. It's always up until the squares. Alright? The reason for that, I'm not too sure. I think it gets really, really difficult afterwards, and it's not really that important to us either as engineers. However, this stuff is actually quite important. Sort of important. Construct a Taylor series up to the quadratic term about the point pi on 4 and pi on 2. So if you guys remember, the Taylor series formula was f of x, y equal to around a point AB. So about point AB it should be f of AB plus x minus a f x AB plus y minus b f of y AB plus 1 over 2 factorial of x minus a all squared f x x AB, and I'll quickly explain what f x x, f x, and f y are, plus 2 times, I need more space, 2 times x minus a, y minus b of f of x, y, a, b, plus y minus b all squared f of y, a, b. Okay? So pretty much, fx ab is the first partial derivative of f with respect to a. So you say that fx is equal to partial differential of f with respect to x. And when I sub in ab, I write fx of ab. So this is the same thing as f AB. I think I've got the notation right, something like that. So whatever expression we get after we differentiate, we just sub in AB. Okay. And similarly, this is the first derivative with respect to y. This is the second derivative with respect to x. This is the mixed derivative with respect to x and y. And this is the double derivative with respect to y. Okay. So what I like to do for these Taylor series questions, what I like to do, I like to make it quite organized. So FAB, or in our case, pi on 4, pi on 2. I like to find what this is, because our fxy is equal to sine x cos y. When we sub in y is equal to pi on 2, this cos term becomes a 0, so we'll end up getting 0. Okay, so that's the very first term already done and dusted. Alright, next I'm going to find each of the derivatives. Alright, so first of all, fx is equal to cos x cos y. Fy is equal to minus sine x sine y. Fxx, so we're differentiating this again, you get minus sine x cos y. Fyy, you get minus sine x cos y. Is it the same? Yeah, it is. Okay, cool. And then you get fxy, which is minus cos of x sine of y. Okay, so now that we found all of our derivatives, I'm just going to sub in AB, or in our case, pi on 4 and pi on 2. So fx of AB is equal to 0. Fy of AB is equal to minus 1 over root 2. Fx of AB is equal to 0. Fy of AB is equal to 0. Fxy of AB, so I'll just say where AB is equal to pi on 4, pi on 2. Fxy of AB is equal to minus 1 over root 2. Okay? So immediately, a bunch of the terms cancel out. This becomes 0, this becomes 0, this becomes 0, and this becomes 0. Alright? So we're left with this term and this term only. Therefore, we can say that f of xy is approximately, remember Taylor series is just an approximation, right? It's not exact. So it's approximately equal to y minus pi on 2 f of y, fy of AB, which is minus 1 over root 2, plus a half of x minus a, so x minus pi over 4, y minus pi over 2 of fxy AB, so times minus 1 over root 2. Honestly, you can just leave your answer like that. Oh, I forgot the times 2. Oops. 2 times. Yeah. You can leave your answer like that and it's completely fine. Okay? And this is pretty much what I've got here as well. Exact same thing. Okay. Part B. Let's take a look. So let me quickly go to my notes. Vector fields. And we're taking a look at this thing over here. So they've given us a vector field F, right? And we have to calculate I forgot what it's called. We have to use a differential operator to find the divergence and the curl of F as well, I think. Yeah, the divergence and the curl. So this is the divergence, and this is the curl. Okay, let's do that. So first of all, we're going to dot product our differential operator with our F vector field. So remember, this upside down triangle is actually a vector times F, which is equal to, okay, I need a much larger vector. This is y, and this is for z. What do we have? X to the 4, y to the 4, x to the 4, y to the 4, and then 4z, 3 minus x cubed. 4z, 3 minus x cubed minus y cubed. Let me check if that's correct. Yep, x cubed minus y cubed. Okay. So if you want to dot product this, you can just expand it out. Can you even hear me? Hello? Okay, yeah, okay, it's working. Cool. Okay, so this is equal to 4x cubed plus 4y cubed plus 4 times 3 minus x cubed minus y cubed, and we're just left with 12. Okay, this cancels out with this, and this cancels out with this. We're just left with 12. Okay, time to find the curl. Cross product with f. So just be going down here. I vector, j vector, k vector, and down here we have x to the 4, y to the 4, and then 4z 3 minus x cubed minus y cubed. Cool. Now, how do we do this? How do we find the determinant of this matrix? I'm not sure how the lecture actually went through it, but this is how I like to do it. So first of all, we take the I vector, and once we take the I vector, we can pretty much cross out this column, right? And then we find the determinant of this 2 by 2 matrix down here. So we are taking the I vector, crossing out these two columns actually, and now we're just trying to find the determinant of this, what is this? Of this 2 by 2 matrix, right? So finding the determinant of this 2 by 2 matrix, you do this this multiplied by with this minus this multiplied with this. I'll quickly show you what I mean. Delta on delta y of 4z 3 minus x cubed minus y cubed minus delta on delta z of y to the 4. Next, minus j. That's just a rule. So we're taking this column and this column out of the equation, and we pretty much form a matrix with this column and this column, and we solve a determinant using that as well. Okay, I'll quickly show you what I mean. So sack this and this. We're gonna do this differential of this minus this differential of this, if that makes sense. So delta on delta x of 4z of 3 minus x cubed minus y cubed minus delta on delta z of x to the 4. Finally, k. Again, get rid of this column and this column, and we do the matrix, do the determinant of that 2 by 2 matrix. So you just get 0, but delta on delta x times y4 minus delta on delta y of x to the 4. Okay, so a few things become 0, 0, 0, 0, and 0. And so if you were to find the curl of f, which is a vector by the way, so the curl is a vector, the divergence is a number, you get delta on delta y. I'll just do in terms of I, so I'll just do 3 minus x cubed minus y cubed of I minus minus delta on delta x of 4z 3 minus x cubed minus y cubed plus this j plus 0k. So you end up getting 12zy squared, 12zx squared, 0. Hopefully that's correct. And that's how you find the covector. If you guys really don't understand what I did here, don't stress. How does he go through it? Oh, he does the same thing actually. There's also a formula for it somewhere. So yeah, so you can use this formula. Alright, that's if you're able to memorize it. If not, you can sort of memorize my method of what I did, and you should get the same answer regardless. Okay, next question. Let me go through this question now. So this is an ODE question. The amount of chemicals mixed into a pond can be modeled using the following ODE given here. Where Q of t is the amount present at time t, and they've also given us an initial condition at time equals 0. The amount present is equal to 0 as well. So at t equals 0, Q is equal to 0. So this linear first order ODE can be simplified by multiplying the integrating factor, and the equation becomes this over here. Enter the integration factor below. So quickly I'll go over a general formula. So if you have dy over dx plus p of x times y, which is equal to q of x, our integrating factor r of x will equal to e to the power of the integral of p of x dx, and there won't be any constant that you need to worry about. Okay, you can just omit the constant, assume it is 0. Okay, so similarly over here, if you want to find the integrating factor p of t, this is just e to the power of whatever is before q. So in this case, we're treating y like q. So this is the y essentially, right? And you're taking this function over here. It might just be a number, but that's also a function. If that makes sense. Right. So you can just do e to the power of a half dt, which is equal to a half e to the power of t over 2. That is our integrating factor. Okay, hence, did you say hence? Oh no, solve the ODE and enter Q of t below. Okay, you may find the following formula helpful. In fact, not just helpful, it's going to be really helpful. Okay, and I'll quickly show you how to find Q of t. So we're definitely going to be using this formula over here. Okay, and in a general sense, again, in terms of y and x, you can say that y is equal to 1 over r of x times the integral of r of x, q of x, dx. Okay, so in this case, we're going to be doing q is equal to 1 over p of t times p of t times 8 times 2 plus sine 4t dt. Okay, so this is our q of t. So this is our q of x or t, right? And you can pretty much just rearrange this formula that they've given us, right? You integrate both sides, this differential cancels out, and you're integrating p of t times 8 times 2 plus 2 sine of t, 4t. And then if you want to find q of t, you just divide by p of t, right? It's a bit long, just a tad bit long, but I'll quickly show you how to do it. So, as I said earlier, p of t is equal to e to the t over 2. Q of t, I'll quickly show you what I meant actually. d over dt of p of t q of t is equal to p of t times 8 2 plus sine 4t. So when we integrate both sides with respect to t, right, so dt dt, this integral actually cancels out with the differential, and we're left with P of t times Q of t is equal to the integral of P of t times 8 times 2 plus sine 40 dt. And if you want to find Q of t, you just divide by P of t. Alright, so we're gonna be using this formula. Alright. So pretty much Q of t is equal to e to the power of t on 2 minus t on 2, because when you divide an exponential, you get a minus in the power of the integral of e to the power of t on 2 times 8 times 2 plus sine 4t dt. Cool. So I'm actually going to break this integral up. So t of 2 of the integral of 16 e to the t of 2 dt plus e to the minus t on 2 8 e to the t on 2 times sine 4t dt. Okay, I want to do this one by one as I did earlier. So this integral, I'll say 1, I'm using the color 1, and I'll say 2. 1 is actually pretty simple. The integral of 16 e to the t on 2 dt, you just get 32, what do you get? 32 e to the t on 2 plus c. Is that right? Yeah, that's correct. Let me check actually. Yeah, good enough. And then 2, you get the integral of 8 e to the t on 2 sine of 4t dt. And this is when we're going to need to use this huge formula here. So I'm going to quickly copy this formula down. So I'll bring it over here so it's easy to see. I'll just take the 8 outside. So don't worry about the 8. I'll take the 8 to the outside. So over here. I'll take it out over here. So this thing over here is equal to, alpha is equal to, in our case, alpha is equal to 1/2, yeah, and beta is equal to 4. So we get e to the power of 1/2 t divided by 16 plus 1/4 times by minus 4 cos of 4x plus 1/2 sine of 4x plus c. That's it. But now to find c is a different story. I can get rid of the c over here. I'll treat it as one combined constant, right? So let's say therefore q of t is equal to e to the power of minus t on 2 of what do you get? 32 e to the t on 2 plus e to the t on 2 over 16 plus 1 over 4. I need my calculator. 16 plus 1 over 4, 65 over 4 times minus 4 cos of 4x plus 1/2 sine of 4t plus c. So technically this should be t, sorry, 4t. Okay. Beautiful. Now expanding everything out, you just get 32 plus 4 over 65 times minus 4 cos of 4t plus a half sine of 4t plus c e to the power of minus t on 2. Now to find c, we just let t equal to 0. So let t equal to 0, therefore we let q equal to 0. Right? So you get 0 is equal to 32 plus 4 over 65 minus 4 plus 0 plus c, and therefore c, I'll just say over here, c we get to be minus 16 over 64 plus 32. Minus 127 over 4. I'm getting a different answer to what I had earlier. Oh, that's because I put 64 instead of 65. 65. So I get, yeah, that's correct. Minus 2064 all over 65. And therefore, Q of t is equal to 32 plus 4 over 65, a half sine of 4t minus 4 cos of 4t plus, minus 2064 over 65 e to the power of minus t over 2. Yeah, it should be like this. Okay, that's an ODE question done. Moving on. So this is the other solution I had, which is incorrect. Move that out of the way. Next question is the extreme values question. This is a very good question. There's a few tricks that you guys are actually going to have to take note of. What I'll do, I'll take a screenshot of this. Okay, so we have f of xy is equal to x cubed y cubed, and it lies on the line. Oh, sorry. Find the extreme values of f on the line x plus y equals to 5. So this over here is our constraint. Okay, so our constraint g of xy is equal to x plus y minus 5, which is equal to 0. Our constraint is always equal to 0, right? At the points where they intersect, essentially. Yeah, okay. So enter the coordinates of the local maximum and the local minimum, and separate them by commas. Okay, chill. So as you guys might know, for Lagrange multipliers, you're going to have to form a function of 3 variables, or might be 4 sometimes, but in this case it's just 3. You do f of xy minus lambda g of xy, which is equal to x cubed y cubed minus lambda x plus y minus 5. Okay, that's the first step. So step 1, done. Second step, you're going to have to differentiate with respect to x, y, and lambda, all 3 of them, so you have to do partial differentiation. So Lx, the subscript notation, I'm using it again, you get 3x squared y cubed minus lambda. Y, you get 3x cubed y squared minus lambda. L lambda is equal to minus x plus y minus 5. So pretty much gives us g of x, g of xy is equal to 0. So that just really doesn't prove anything, but we're going to need to use it later on to find our values for x and y. So pretty much, no, I won't say that. I'll say that x plus y is equal to 5. So we're gonna solve all three of these simultaneously to find x and y, and the maximum or minimum values, right? So first of all, I'm gonna say this and this. Lambda is equal to 3x squared y cubed. Lambda is equal to 3x cubed y squared. Now, using simultaneous equations, so I'm gonna say solve simultaneously, you get 3x squared y cubed is equal to 3x cubed y squared. Taking everything to one side, you can just cancel out x squared and y squared on both sides. However, there's something that you're gonna have to take note of. That you might miss a solution if you do that, and I'll show you what I mean. So if I do that, this and this, this and that, so you get y is equal to x, right? So you only get one solution. However, that's incorrect because we actually have multiple solutions. So you get 3x squared y cubed minus 3x cubed y squared is equal to 0. 3x squared y squared, and then you get y minus x equals 0. So you get x equals 0, y equals 0, and x is equal to y. So you get different solutions. Essentially, it's the same solution except x equals 0, y equals 0. Right? So you can just say this is equal to y. Right? Essentially the same thing, except in this case we didn't take into account x is equal to 0 and y equals to 0. Okay? And also when you're dividing both sides, you can't divide by 0, so that's why you might miss a solution. Okay? Alright, now solving these simultaneously using this equation over here, let's say equation number 3. So using 3, you get x plus x is equal to 5, x is equal to 5 on 2, y plus y is equal to 5, you get y is equal to 5 on 2. Then you get, so that's for solving x and y solutions. Wait, how do I explain this? So we know there's already one solution at x equals to 0 and y equals to 0. However, when you sub that into our function f, you get just 0, right? So that can't possibly, it could be a maximum, but however, we're trying to find some other solutions as well, right? So now that we know the solutions for x equals to y, where y and x is equal to 5 and 2, we can say that f of 5 on 2 is equal to 5 on 2 cubed, 5 on 2 cubed, which you get to be 15625 divided by 64. So this is the value of our maximum. Maximum when x equals to 5 on 2, y is equal to 5 on 2. Okay, so I'll quickly go through what I've done. So I found that this is a solution and this is a solution, right? But x equals to y can literally be any value. You can let x equal to 1 and y equal to 1, right? How do you know if that's the maximum, right? You're not sure if it's a maximum or a minimum, right? So this is why we use this third equation here, right? The constraint. Because we're looking at a constraint on a certain other curve, right? You can find the maximum on that constraint curve, right? So you've already found something for x equals to y, right? What some questions do is that you find x in terms of lambda, right, or y in terms of lambda, and you sub it in x and y in terms of lambda into this constraint equation, and you find values for lambda, and then you just go back and do back substitution to find x and y values. However, in this case, we've just straight up found x and y straight away. We don't need to really find lambda. We've already found what x and y are, and we know that x is equal to y, so the maximum value occurs when x is equal to y. And that's why I found that these are the maximum values. Oh, this is the point at where the maximum occurs. And so I can pretty much assume that this is the value of the maximum when x equals to 5 and 2 and y equals to 5 and 2. But the second part is asking enter the only value of the local minimum. And one thing to note, if we let x is equal to y, oh no, I just want to ask, actually, oh, there's no one to ask, but this can't ever be negative, if that makes sense. This function f(x,y) can't ever be negative. The reason being because we know that x equals to y is a solution, right? So if we let x equal to be a negative number and y be a negative number, because it's to the power of 3, x cubed will be negative, y cubed will also be negative. Negative multiplied by a negative, you get a positive, right? So no matter what, this function can never be a negative number, right? And obviously if you sub in x and y as a positive number, you'll always get a positive number, right? So the minimum value occurs at x equals to 0, y equals to 0. Because it never goes below that. It's always, that is the minimum value, and it's always above that value. So it's always greater than 0, but never less than 0. So we can say that minimum occurs at x equals to y, which equals 0, and therefore f minimum is just 0. Okay, this one, just got to think about it a little bit. Next question. Ah, matrices question. I think this might be the last question that I go through, because I don't have much time. I really want to go through this question as well, but I'll see what I can do. So, consider the matrix M. So 1, 1, 4, 1. Calculate and enter the eigenvalues of the matrix M, where lambda 1 is less than 2, or lambda 2. Okay. So the way you wanna find eigenvalues is you wanna find the determinant of m minus lambda I, which is equal to 0. So you wanna find the determinant and let it equal to 0. Right. This is the rule from 1131 or 1141 math. Right. So what I've done pretty much, I found the determinant. Right. This over here is m minus lambda I, and now I'm just trying to find the determinant of that. And you get two values. You get lambda equals to 3 and minus 1. So you can essentially say that lambda 1 is equal to minus 1 and lambda 2 is equal to 3. Because they said lambda 2 is greater, right? Yeah, lambda 2 is greater. So these are answers. I'll keep that up for a second. Oh, dude, I think I broke the chair. It's fine. Second part of the question. Hence, solve the initial value problem. So you're pretty much solving differential equations using matrices, or this is called a system of ODEs. It's not overly difficult, right? Pretty much, they've given us two differential equations over here. Dx over dt is equal to x plus y with initial values, so initial values, IVs over here, right? And dy on dt is equal to 4x plus y. Okay, you're going to have to use matrices for this question. So what I've done, I've put into a vector form. So dx on dt, dy over dt, right? And I've kind of skipped up the solution here. So so this is equal to x plus y, and this is equal to 4x plus y. Okay, and if you want to put this in terms of a matrix and a vector, yeah, it will look like this. So this is 4x plus y. This is x plus y. Okay. Reason for that is we're going to take the dot product of this and this. So this is a vector, this is a vector, and you end up getting x plus y. If you take the dot product of this and this, so 4, 1, and x, y, you get 4x plus y. Okay. So you can pretty much just take a look at the coefficients, 1, 1, 1, and 4, and you can pretty much just form a matrix like that as well. Okay, now to actually solve the system of ODEs, we're going to need to use this formula, right? So in the case of 2 by 2 matrix, use this one, but if there's also a third row and column, you're going to have to use this one over here. But I'll just get rid of it because it's not relevant to the question. So what we're going to need to do to solve the differential equations, you're going to need to use this formula where lambda 1 is our first eigenvalue, lambda 2 is our second eigenvalue, v1 is the eigenvector for lambda 1, v2 is the eigenvector for lambda 2. Okay, so and I'll quickly show you how to find the eigenvectors, right? So for lambda equals to 3, you're gonna have to set up this equation: m minus lambda I. Oh, it should be an I. Sorry, it should be an I as well. Lambda I multiplied by the vector v. But I'm just gonna let v be any vector v1, v2. Just a bit of revision from MATH2018. So you end up with this matrix using this where lambda is equal to 3. So I'm just gonna say 3. Let's see, 3. And using Gaussian elimination, we get minus 2, 1, 0, 0 as our matrix, and we're gonna pretty much just solve it, right, using v. So what I'm doing here, this is a terrible explanation, but I'll make it a bit more easy to understand. And this is equal to the 0 vector, right? So the 0 vector, and pretty much we're solving that. We're solving this row over here. So this multiplied by this is equal to 0, and similarly this multiplied by this is equal to 0. But that's pretty obvious, right? So we don't really worry about the second row. We only worry about the first row. So minus 2v1 plus v2 is equal to 0. Let v1 is equal to t. Okay, this is a trick that you're gonna have to use to find the eigenvectors. So eigenvector is, you don't really need to find, it's sort of a direction, if that makes sense. So if we end up with v equals to t1, 2 vector, this vector over here, right, the direction that it's facing, which is 1, 2, that is our eigenvector. Okay, the direction that our v vector. So we're solving for v essentially, right? So what we're doing all the way over here from down to here is we're solving for v, the vector v, but our eigenvector is just the direction that that v is pointing. And because t is just a constant, so I'll just say constant, right? The direction that it's facing is 1, 2. Similarly over here for minus 1, you end up getting your eigenvector for minus 1, so I've just put subscript to minus 1 to show that the eigenvector of minus 1 is equal to 1 minus 2. Right? Now, subbing this into our large red equation over here, it's not that large, but you end up getting this. So our vector y, which I let it equal to xy, yeah, let it to xy, is equal to our constant c1 multiply eigenvector plus e to the power of 3t plus c2, our eigenvector for minus 1, and to the power of minus t. What we can do now is we can actually split it up, find x, and then we can find y. We can find two equations, for one for y and one for x. So it's going to be c1 times 1 times e to the power of 3t plus c2 times 1 times e to the minus t, which I've got over here. Similarly for y, it's going to be c1 plus 2 times e to the 3t plus c2 times minus 2 plus times e to the minus t, right? So we get two formulas for x and t. So we pretty much come to the final answer, except we don't know what C1 is and we don't know what C2 is. To find them, we're going to need to use our initial values. So they've given us that at t equals 0, x is equal to 5. At t equals 0, y is equal to 6. So I've set up some simultaneous equations over here. Alright, and you end up with C1 is equal to 4 and C2 is equal to 1. So our final answer we just get to be x of t is equal to 4 e to the power of 3t plus e to the power of minus t. Yt is equal to 8 e to the power of 3t minus 2 e to the power of minus t. Cool. Leah, do we have this room booked? Do we have this room booked? Cool. Yeah, just put some shit up on the thing, that's why. It's a bit concerning. Yeah. Okay, cool. Next question. This one you're going to use Laplace transform. Since I've already gone up and I don't have that much time, the steps are essentially the same, except instead of using ODEs and matrices, you're going to use Laplace transforms. So you guys can take a pause and take a read through of what I'm doing here. So this is from the table over here. So this is from the table. I'm using this one over here. And then you form matrices based on what I've done previously. And then you're going to need to use simultaneous equations to find x of s and y of s as well. And then to find x of t, you're going to need to do inverse Laplace transform. So that's where the partial fractions actually comes in. Because I don't have that much time, I'm going to skip over this question. However, I should already have solutions to it somewhere. Let me take a look. Yeah, these are the solutions to it. So pause and read through it if you want. Oh yeah, I didn't even complete it because you have to use shifting theorem, which is a bit long, but essentially pretty easy. Alrighty, cool. Next question. Okay. So this is using double integration. We're going to need to find the volumes, and they've told us in part A, find the limits of the double integral, and then find the integrand, and then find the volumes, right? This kind of sets us up pretty well. So they've given us a cylinder and then a hyperboloid of 2 sheets. You can kind of think a hyperboloid of 2 sheets as a constraint. And actually, what I've done on Desmos is that I've actually graphed it out for you guys. So this is what it looks like. And what we're trying to do is we're trying to find the volume of this thing over here and this thing over here. So it's only finding 2 volumes, but they're equal. So what you can do is you can find the volume of one of them and then just times it by 2. Alright. Similarly, this is another view of the question. Alright. Graphing it out does help because you see that they both intersect at the point z is equal to 8 and z is equal to minus 8. Right. It does kind of help. When I did this question, I actually didn't see that because this is from my paper, and I was doing all sorts of rubbish and I got it wrong, I'm pretty sure. Okay, that's all good. Now to find the volume, I want A and B, so this is going to be A and B. It's going to be our theta values, which is d theta. So the outer limit is theta, and the inner limits are is going to be R1 and R2. So how do we find theta and R1, R2, right? We're going to have to use, because we're essentially just integrating, we're finding the volume inside this cylinder. Oh, actually no, this is the constraint, sorry, and this is what we're actually integrating. So this is a constraint. And what we're doing pretty much because this is a constraint, our limits will be constrained by this function over here, right? So we know that r is equal to the square root of x squared plus y squared, so r squared is equal to 64, and therefore r is equal to 8. The reason r can't equal to negative 8 is because radius, it's a radius, right? It's a length. You can't have a negative length, essentially, right? It can point in the opposite direction, but the actual length is in minus 8. Also, you can see that r is equal to positive square root of x squared plus y squared, right? So you can't even get a negative here anyways, because a square root can't be negative, right? And now what I've done, I've drawn a top view of the actual cylinder, so similarly to here. So I've drawn this top view over here, where r, the lowest, the lower limit for r is 0, and the maximum upper limit is 8, right? And we know theta, this r can go around the whole circle. The r can go around the whole circle like this. So theta essentially is from 0, and it can go all the way around 2 pi, right? So lower limit for theta is 0, and upper limit is 2 pi. Lower limit for r is 0, and upper limit is 8, right? So that's what I've done over here. So you can pretty much just say that 0, 2 pi, 0, 8. Right? And to find the integrand, as I've said, we're actually integrating this function over here, right? This is just a constraint, but it kind of makes sense because if you take a look at this diagram, we're integrating this hyperbola. We're trying to find the volume of this hyperbola within the cylinder, right? The cylinder's just there, right? It's just constraining it up until here and here, right? However, we're actually finding the volume of the cylinder, right? So we're gonna have to integrate this function over here using polar coordinates, right? And similarly, as I said earlier, x squared plus y squared is equal to r squared, so this is just r squared plus 64. So we're gonna have to find what z is, and I've already shown here. Oh shit. We need to convert z squared to polar. So z is equal to the square root of r squared plus 64, right? So that's the function, right? But that's not f. The reason why we multiply by r is if you take a look down here, right? This is how we find the volume in Cartesian form. So we have limits y1, y2, x2, x1, the function xy, and dA. So dA is equal to dx times dy, right? Oh, also by the way, this is also equal to z, right? But dx on dy, and it's also equal to r dr d theta. So if we don't have the r there, we're not really integrating with respect to the proper area or the volume, right? Some people actually like to do it like this. Right? It's a bit more general. So yeah, we don't have the r there. We have the function z, but we have to multiply by r so we can attain this dr d theta. So that is why the function is r times z. But as I said earlier, that we can find it once and then we multiply by 2, right? This one over here, z, is a positive because it's above the z-axis, so it's in the positive z-axis, right? However, this one is in the negative z-axis, right? So if you want to do them separately, what you can do is that you can find z. Let's say z1 is equal to this, and z2 is equal to minus square root of r squared plus 64, right? But because I've said earlier that the volumes are the same, you can just get rid of that and just do 2 times r squared plus 64, square root of r squared plus 64. So that's why we have the 2 there, and the r, as I've said before, we need to find this r dr d theta. Right? Or else we can't really integrate it. Right? It's not really correct. Okay, hopefully that makes sense. So over here, I've kind of done the integral for you guys. So this is our f. Right, and this is just solving the integral. I would think it's a much nicer answer, but I didn't get a really nice answer. This is the answer I got. It's not that nice. And obviously it should be units cubed. And I've also used sub midway through. You don't need to. It's just that I couldn't really wrap my head around the integral, so I just made it a bit simpler for myself. Is there a mistake? There might be. This step is correct 100%, and then I might have made a mistake somewhere down here along the lines, but because I don't think it should be that disgusting of a number. But if this is correct, that's the answer. I don't really need to go over actually integrating the thing. Hopefully you guys can do that. It's not too hard. We've done it in MATH2018 a lot of times, and throughout this course as well, multiple times. So I just wanted to go through the theory behind where f and the limits come from. Right. However, for part B, I will actually explain it. So we have calculate the volume bounded by the planes z is equal to 12 minus 3x minus 2y, and z is equal to 1 over 3, 12 minus 3x minus 2y, right? And in the first octant, so the first octant pretty much just means let me draw an octant out. Here. Huge C as well, but yeah, that's just the lower quadrant. But hey, pretend that's the upper. So this is for zx. Z is above 0. So there'll also be some stuff down here. Something like that. Alright, blah, blah, blah. And first octant is pretty much just in this first quadrant. So over here. Alright, so this is where x is greater than equal to 0, y is greater than equal to 0, and z is greater than equal to 0. Right. So you can just pretty much just think about it like this. Yeah, kind of thing. I'm just recording a video.
You're recording?
Yeah. So.
That's what I bought.
Okay, yeah, I'll do it after this video.
Oh,
No, I'm still recording, dude. Yeah. Yeah, so this is pretty much what's the first octant looks like. So this is y, z, y, and x, and you're pretty much just looking at the positive quadrant, essentially, because as you know, in normal Cartesian plane, this is the positive quadrant. In this case, because it's 3D, we're looking at octants, right? I really didn't need to go over that, but anyways, in the first octant, blah, 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 we have to firstly find the point of intersection. You get this. And to find the actual volume, yeah, within our area specified, you have to do z1 minus z2, which is the area, the volume above minus the volume below, times dA, where dA is equal to dx dy. Right? So I found the area of intersection, or the area which we're integrating within. So I've denoted this as ohm, and this is pretty much the area that we're integrating in. After you double integrate the area, you end up getting the volume. Right? So since I've done dx dy, the outer limits is just going to be between 0 and 4. The inner limits, however, it's a bit different, right? Because it actually changes with respect to the function y, or it's a function with respect to x, right? So it actually changes. So we're going to have to find what the value of x here is along this line over here, along this line. Because x varies, it's just equal to 4 minus 2y over 3. And you subbed it in, and you get your integral, blah blah blah. Okay, this last question I don't really have time going through, but there are solutions to it. The lecture I went through a very similar question in the lectures. So something like, yeah, this question right here, very similar question. And you might want to take a look at PDE's wave equation. Yeah, this is a very similar question as well. All of this is pretty much exactly the same thing as he's going through in the question. Okay, there's one more thing that I'm missing. Further PDs? Yeah, this question over here as well. So I don't have solutions to it, but solutions are online. Alright, cool. I'll end it there for now. Best of luck for your exam. Hopefully this was helpful. I don't know if you can ask me any questions. I probably won't be free anyways, but yeah, good luck and bye bye.